Today, my teammate and I will introduce a new topic based on TCP to you, that is, explicit congestion notification, also known as ECN. Let's get started. Firstly, in order to know why we need ECN, we need to know the problems of the congestion control, which we have learned in this semester. From this semester's study, we know that transmission control protocol, host-based congestion control mechanisms have been key to the robustness of the Internet. However, I have to say, there are some problems of congestion control. The first limitation is its low efficiency in high bandwidth and high latency network. With the development of networks, the bandwidth has increased from 100 MB to 1 GB, even to 10 GB per second. As a result, bandwidth delay products of the network can become huge. But because the sending window of TCP is the minimum value between the congestion window and the receiving window, the value is really limited. As a result, the efficiency of TCP is also low. The second problem is invalid assumption in high-speed network. Traditional TCP always interprets packet loss as network congestion and assumes that packet loss caused by link errors is negligible, which is not valid in high-speed internet. The third problem is about an increasing number of data-sensitive applications. We know that audio and video basically use UDP to transmit data, while UDP does not provide data reliability guarantee. If packet loss is caused, TCP will not take responsibility, and UDP will continue to transmit. Hence, the speed of TCP transportation is really low. Then, let's see the ways to improve congestion control. Traditionally, there are mainly two ways: congestion control algorithm based on packet loss and the congestion control algorithm based on delay policy. The first way is to modify congestion control algorithm based on packet loss. That is, these algorithms don't change the assumption about packet loss, but they may change the variables and avoid congestion so that the window remains in a large enough range to fully utilize the bandwidth. However, these algorithms also have limitation. That is, although it can greatly improve network bandwidth utilization, it also means the next congestion packet loss event is not far away. Then let's look at the second way. It's algorithms based on delay policy, such as TCP Vegas. It judges whether the network is overloaded by the growth trend of the policy difference of the arrival time of each group of packets. However, these algorithms also have problems. They are not fair. Based on the two main ways, there are some other algorithms, for instance, BBR and ECN. These algorithms inherited the idea of the previous two algorithms and may achieve better. Today, we'll discuss ECN, also known as explicit congestion notification. This is today's focus. Firstly, let me introduce ECN to you. ECN is not a congestion control algorithm like slow starts and AIMD, which we have learned in this semester. It only has one function, that is, to inform the sender about congestion so that the packet read can be slower in order to allow the congestion to clear. There is also one thing that you need to pay attention to. ECN must be enabled on both endpoints and on all of the intermediate devices between the endpoints for ECN to work properly. Any device in the transmission path that does not support ECN breaks the end-to-end ECN functionality. And then I'll show you how ECN works. This figure shows the work of ECN. That is, when the sender sends the packets to the routers, and maybe sometimes congestion happens, the router will mark this packet instead of dropping it. And then the package will continue to move, and maybe it will reach the host. And then the receiver may notice that the packet is marked. So it understands that there is congestion in the halfway. And then it will send congestion signal to the sender and informs TCP sender of the congestion. Then, and my teammate will introduce the next part.
Well, my name is Xingxiong and my net ID is UIUC 24. And I'll be talking about the next part in our presentation. So the first thing I'll be talking about is why is ECN a good idea? So since ECN marks packets before congestion actually occurs, this is useful for protocols like TCP that are sensitive to even a single packet loss. Upon receipt of the congestion marked packet, the TCP receiver informs the sender about the incipient congestion, which in turn will trigger the congestion avoidance algorithms at the sender. So if you look at these figures, these are the figures indicates the WAN simulations with a 100 millisecond TCP clock and a large number of bulk data connections. We can note that for both drop tail gateways and red gateways without ECN, the tailnet packet delay is worse with a large number of bulk data connections or with TCP connections with larger windows. So in these simulations with increased demand, an increased number of packet drops is required from a non-ECN gateway to control congestions. And next up, we'll be talking about the advantages of ECN. So we divided it into 6 parts. So the first thing is that it improves the throughput. So ECN seeks to avoid the inefficiency of dropping data that has already made it across at least part of the network path. So ECN can improve the throughput of an application. And the second part is that it can help reduce the head of line blocking. So by enabling ECN, transport continues to receive in-order data when there is an incipient congestion and can pass this data to the receiving application. So the use of ECN can avoid the additional reordering delay in a reliable transport. And next up, it can help reduce probability of RTO expiry. So the benefit of avoiding retransmission loss is expected to be significant when ECN is used on TCP, on a TCP SYN or ACK packets where the RTO intervals might be large because TCP cannot base the timeout period on prior RTT measurements from the same connections. And also, applications that do not retransmit lost packets, the ECN can help them. So for this scenario, a transport that enables ECN can receive timely congestion signals without the need to retransmit packets each time it receives a congestion signal. And what's more, also the ECN can make incipient congestion visible. So a characteristic of using ECN is that it can expose the presence of congestion on the network path to the transport and network layers, thus allowing information to be collected about the presence of incipient congestion. So lastly, the opportunities for new transport mechanisms. So for ECN, it can enable design and deployment of new algorithms in network devices and internet transports. So for internet transports, it needs to regard both loss and CE marking as an indication of congestion. However, while the amount of feedback provided by drop ought to naturally be minimized, this is not the case for ECN. In contrast, an ECN capable network device could provide richer or more frequent fine grained indication of its congestion state to the transport. And that's all we talk about the advantage of ECN. And next up, we'll be talking about the disadvantages of ECN. So we divide it into two parts, which is non-compliant ECN connections and also the potential loss of ECN message in the network. So the first thing is that for non-compliant TCP connection, they could set ECN field to indicate it was ECN capable, and then they can ignore ECN notifications. And what's more worth mentioning is that for a network that uses only packet drops for congestion notification, a non-compliant connection could also refrain them from making appropriate window decreases in response to that packet drops. So in a word, a non-compliant connection could cause congestion problem in either ECN or non-ECN environment. So that's not a special case for ECN, but it still is an advantage. And also the second part is that an ECN message has no counterpart with packet drops in that an ECN message can be dropped by the network. So the congestion notification could fail to reach the end node. But however, what's mentioning is that with red gateways and the gateway does not rely on the source to respond to each congestion notification, the gateway will continue to set the ECN field and randomly choose packets as long as the congestion persists at the gateway. So the occasional loss of ECN message should not be a serious problem. And lastly, let's look at the application of ECN. And this is one of the case I found from one of the papers, which I will show you at the last slide. So this is the image of that simulation structure. In this paper, it categorizes traffic into the following two groups, according to the way the traffic handles congestion. So bulk data TCP flows and cross data CBR flows sent from the left to the right over the network shown in the figure. And these are the two results that has been simulated from this case. So the first figure is the simulation without UDP traffic, which is light congestion, and the second image is the simulation with UDP traffic, which means heavy congestion. So in these two tables, the left table reports non-improvement from using ECN for each delay value, as we can see from these pictures. So for some part, it lowers the delay. For the other part, it kind of makes the delay even more. But for the right part, it reports a better performance using ECN in comparison to red for each delay value. For each delay value, the red with ECN support continuously getting better performance in the simulation. And That's all we will be talking about in this presentation. And here's the citation that we use in this presentation. Finally, thank you for listening for our presentation.